Okay, I'm going to restart OneNote. Okay. Hey, I'm so embarrassed down here. I do apologize. Okay, probably this software has an update and the update did something stupid. Oh, God, Lord Mighty. What a waste of time.
Prof, I found something. I think it works on mine as well. So if you
Yep.
go in under typing, no, in settings, if you go to typing,
Settings? Where?
no, settings of the
Ah,
of Windows. So
yeah.
yeah,
Okay.
settings,
Yes.
oh, devices,
Devices.
typing.
Typing.
If you scroll down, there's touch typing. Yeah. So on top, above hardware keyboard, yeah, the option, yep, that one. Just turn that off.
Oh. Okay. So I'll restart this again. Okay. I do apologize. With this. Okay. So hopefully this will work now. Okay. It's okay. Now I cannot erase. It's okay. It's not important. Okay. So, okay, coming back to square. Thank you so much. Okay. Don't know what work yet, but okay. So knowing that a given shearing stress V cause a maximum shear stress of 10 psi in the head shear extrusion shown, determine the corresponding shear stress at point A and point B. So we want to find the stresses at point A. Okay, we want to find the shearing stress at point A and the shearing stress at point where? At point B. Okay. So we are going to use our 5 rules. Okay, we're going to use our 5 rules, right? So you all can recap our 5 rules. Number 1 is V and I are constants, right? So if we were to write the formula out, okay, we were to write the formula out. Okay, we have to write our formula out. So if we have to write our formula out, which is shear stress is equal to VQ over IT. Right? We have this formula. So just to quickly recap, right? Rule number 1, V and I are what? Are constant. Okay, just to quickly recap, V and I are constant. So regardless of point A or point C, V and I will always be what? V and I will always be constant. Okay. So now if we come back to now I cannot move my screen. It's okay. When I touch, oh God, Lord Mighty. Where's my cursor? Right. So whether we find point B or point A, all will be what? All will be constant. So I'm going to draw our centroid now, position of our centroid. Okay. So this is the position of our centroid. Right. So this is the position of centroid. So this is our centroid. Okay, that is the position. So remember the other rule that we have, right? That rule number 2, right, is the datum is at the centroid. Okay, and then rule number 3, right? Analysis will start at Y max, right? Rule number 4, the first moment of area cannot cross the centroid. And then we come with another rule, right? We came with another rule, is that rule number 5, right, is that the web controls the shear flow, right? The web controls the shear flow. Okay, right? So now with this in mind, right? With this in mind now, okay. Now let's say now we want to find stresses at point B. Okay, we want to find stresses at point B. Okay, so we want to find the shear stress at point B. Okay, so we know that we have a Vy. Okay, so let me address some transformation first. Okay, so this is our Y, this is our Z. Okay, so this is our Vy. All right, that's our Vy. So now I'm going to construct the Q, okay, the shear flow. Now, on this diagram over here, which I did not mention, you can see, right, the shear flow over here, the length is longer than the shear flow near to point A. Likewise, for the white flange, the same. Down here, the arrow is bigger. Down here, the arrow is smaller. What this means is the magnitude is bigger. The longer the arrow, yeah, I'll write down here, longer the arrow, the shear flow, Q arrow, correspond to higher, okay, correspond to higher magnitude. Okay, I want to highlight that. Okay, so in this context, right, we are now going to construct our shear flow, right? And how to construct our shear flow is the web. I repeat again, the web controls the what? The direction. So because Vy is coming down, so this is good. So I draw the arrow very much longer. It's because the magnitude is bigger. Okay. You can see that, right? And then at where Vy is, right, the shear flow will do this, right? And then at point A, it will go outwards. Okay. Now, why I pick this problem is this. Okay, why I deliberately pick this problem. So I'm going to get a I'm going to switch software for a bit, just a bit. Okay, I need to go to PowerPoint because you cannot do this in. Okay, I'm going to draw. Bear with me. So I'm going to draw a box. Wait. Copy. And I'm going to paste. Okay, so this is our box. So now, if I cover the bottom part, okay, because point B is at the top, right? And we know that the first moment of area cannot cross the centroid, right? So when I cover the top, right? Sorry, when I cover the bottom, what you see now is at point B, we are going to apply box beam analysis. Okay, I repeat again, we are going to apply box beam analysis. And where we have our start point over here, right? The Q go on one side to the left, and it goes the other side towards the what? Towards the right. So when that's the case, when we apply box beam, because from the terminal, right, we have a terminal, it goes left, and once it goes right, we just put down here 2Q. Okay, because later on we need this 2Q value. Okay, we need to use this 2Q value. Okay, so from here, because it's thin wall, right? Because it's thin wall analysis, T is equal to 0.2 inches. Because the thickness is perpendicular to the shear flow Q. Okay, so the area that we are going to analyze is this area. I'll draw for you now. Okay, it's this area. I'm going to draw for you now. So it is this area that we have to analyze now. Okay, that's the area. Okay, so like anything before, like anything we said before, the most critical part is what is the Q value, right? What is the Q value? The Q value, Eugene. Okay, what is the Q value? Okay, so we are going to now determine the shear flow. Sorry, we are going to determine the Q value. Okay, we're going to determine the Q value. Okay, I mean the first moment of area, right? So the first moment of area, I just shaded to you in orange. Okay, why we have to consider that? Because from the terminal, one of the Q go to the left hand side, one of the Q, the other Q go towards the what? The right hand side. Okay, so the first moment of area Q, capital Q. Okay, so first moment of area. Okay, the first moment of area Q is equal to width, right? Depth and y bar. Okay, so the width, it is, so if I were to remove now where is my, if I were to remove, right, so the distance, the width is what, we can do the width if I cover here, right? So is 2 inch minus by 1.3 both sides. Okay, so 2 minus by twice 0.3 once, 0.3 twice, right? The depth is 0.2. The y bar, because the whole thing, right, the whole thing is 1.5, right? And if you look at this structure, okay, if in terms of area, okay, in terms of area, right, the top area and the bottom area are the same, so the centroid, the y bar is at 1.5. Okay, so this will be equal to 2 minus 0.3 minus 0.3 times 0.2 times 1.5 is equal to 0.42. Wait, no, sorry, I did something. The y bar is not 1.5. What am I doing? Yeah, today I've been thrown off because of the Microsoft. 1.5, right, minus 0.2 divided by 2. I do apologize. Okay, so 1.5 minus by 0.1 times by 0.2 times by 1.4 is 0.392 inches cube. Okay, this is Q. So if you were to ask if I'm going to write this properly,